temperature above 100 degrees, it'll be a gas. When I cool it below 100 degrees C, it's going to turn into a liquid. When it turns into a liquid, what happens to all that empty space? It contracts. So this is going to create a good vacuum. And so I'm going to use steam here versus air because it's going to make a much better vacuum as the gas molecules contract. And so how do I seal it? So now I have hot steam in there. What I'm going to do to seal it is I'm just going to invert it upside down here to seal the mouth of the can. And let's see what happens. Okay, so I want to fill this up with lots of steam. It looks like it's pretty well full of steam, right? Okay, and then let's go ahead and retract that. And so now you can see that this can was really a lot more empty, although that's not even close to a pure vacuum, because a pure vacuum would have crushed this to nothing, basically, almost nothing, because there'd be no gas volume in there. But that's a difference. So here I got a way to get rid of the pressure inside there, you know, and create that vacuum. So that's 14.7 pounds pushing outside, but inside was a lot less than 14. It still wasn't that much less, you know, but quite a bit less. So this is just a show. So gauge, you know, even though the gauge pressure was 0, it's not 0. You know? And so that's does that answer the question? Yeah. So that's what I wanted to show with this. You got to watch out because when you heat the rubber, one thing it could do is it could melt. Which would be, melting is physical or chemical process? Melting, physical. The other thing is it could start to decompose. If it decomposes, is that physical or chemical? That's chemical. Unfortunately, yeah, burnt rubber, I burnt a little bit of it. It doesn't smell so great. All right, today, well, are there other questions? Will I post the answers for the practice test? No. I won't. I'm not going to post the answers for the practice test. There's one reason I don't want to post the answers to the practice test, but maybe for this. The reason I usually don't post the answers to the practice test is because you should know the material well enough that if it's open book, you can check your answer. You know, you want to be at that level where you can, you're able to check the answer, open book. Right? However, if you're still not quite comfortable, you know, because ultimately on a regular test, how do you check your answers? This goes in science. This happened to me when I was pursuing science. When I was pursuing science, there's always somebody who knew the answer. There's always somebody I can ask, did I get the answer right? You know, is this right? There's always somebody checking my answer, right? Until you get to a certain point. And this point you reach faster than you think. The point is that in science, yeah, you got to learn what other people did, but you know, but nobody's going to pay you to repeat. Is somebody going to pay you to repeat Lavoisier's experiments? Even if it's the government, you know, it's the National Science Foundation. Oh, I write a grant. I want to repeat Lavoisier's experiments from chapter 1 of our book. Are they gonna pay tax dollars for that? No. Nobody's gonna pay. The only thing they're gonna pay you for is to do something that nobody's done before. Well, if you do something that nobody's done before, then who has the answers? Who has the correct answer? Did I do this right, or did I do this wrong? And so this is a whole different element. There's no answer key. There's no answer book. How do you check your answers? And so you have to learn how you check your answers, and then you have to, and so the reason I don't post this is because this is part of the process of learning how to check your answers. Because you got to learn how to check your answers, and then you have to defend those answers in front of all your critics, you know, and they're going to be critics because science is full of critics. And so you have to stand up there and defend you don't say, well, you know. And so I know you guys are just starting, and it might be too much, but you know, sooner is the better to start doing this. That way you'll be prepared. And so the reason I don't post it one, you could check the answers as open book, and two, you should know the techniques for answering these, such that if the answer book is wrong, you can say, hey, they did something wrong here. My answer is correct. I went through all the steps. You go through all the steps, you see, I did step A, step B, everything crosses out, everything looks good. My answer should be correct. I double check the calculator. My answer should be correct. Now, our book isn't as bad, but Chem 1A, Chem 1B, there are a huge number of typos in the answer key. There are a lot of wrong answers in there. And the thing is, some students will say, okay, that's a wrong answer, therefore I must have done it wrong. Other students come up to me and say, hey, I did this right. The book is wrong. These books, you can't have 100% faith in books, because books, this is 1,000 pages. You got a limited number of editors, you got a limited number of time. And so the answer, the solutions guide to their Chem 1A book has 5 authors. 5 different authors, they do things different ways. And they check things differently. And some of them, the solutions outright wrong. But, this happens in science, so that's the other thing. Okay, now with that said, we're actually going to go through this exam. I just wanted people to try it, to give it a go, because you want this to be kind of the exam environment, so you can condition, prep you mentally for the test. But since this is the first one, and I see a lot of people haven't gotten to it yet, and they aren't going to have time to get to it, we're going to go through it after I finish chapter 5 today. Everyone should, at least you guys will be going through it, and I'll be helping you along. Okay, I'm not going to post the answer key, but of course, if you ask me about a specific question, I'll tell you, if you got the answer correct or if you got it wrong.
Is Chapter 5 homework due on the test as well?
Chapter 5 homework is due on the test, as well. The Chapter 5 homework, see, Chapter 5 is not much more to Chapter 5, so I was going to go through Chapter 5, and since there's not that much time, and I know you guys don't have that much time, we're going to go through the homework together as well today. And so the plan was to finish up Chapter 5, go through the homework for Chapter 5, which is a pretty short homework assignment, and then go through the test. That'll be a review. But this will be a little different, because I have to keep the pace going. I mean, we're supposed to cover a certain number of chapters, to 19 chapters, so I'm not going to do this for every test, but for this test we will, the first test. All right, so that's why I'm bringing up the homework here, but I want to just finish up Chapter 5 now. But were there other questions you guys had? Ideally, you should be, you go through the test and you go, well, I'm shaky on this problem, I'm shaky on this problem. And when you're shaky on those particular problems, you should go into the book and then read those sections carefully, or go to the homework and do problems that are similar to that, carefully, and then just reinforce your knowledge up to the point where you can be solid, because every single homework problem I've assigned has the answer there. And so if everything you do has the answer there, I'm not doing you a favor. I'm doing you a disservice, actually, which is what a lot of instructors are saying. But I don't agree. I think it's okay. Okay, so where did we leave off? Actually, I didn't get as far this time.
Yeah, we were at
Isotopes right here. All right, so we're talking about the composition, and we need the numbers. So we need to number protons, neutrons, and electrons, and make up these things. And so, did we already talk about the mass number? Yeah. N plus Z. We can put this all together in something called a nuclear symbol, or an isotopic name. And so, nuclear symbol would be something like this. If we look at oxygen, 16-8, like this, that tells me the composition of this atom. The composition of this atom, this 8 is Z, and this is optional because oxygen only has a Z of 8. Oxygen's element number 8, and therefore this is redundant. So a lot of people leave this off, including me. I never write this 8. I just write oxygen 16 because oxygen is element number 8. I don't have it memorized, that it's 8. I just know I can look it up on the periodic table easily. Now the 16 is A. A again is what? A is the mass number, and that is the number of neutrons plus the number of protons. In other words, Z plus N. So we have that. And that will basically tell us the composition. There's also something here that's not shown, and this is the charge, which goes here. The charge in this case is 0. If the charge is 0, we don't write down 0, but sometimes we can have an atom that actually has a positive or negative charge. And when an atom has a positive or negative charge, it has a name associated with it, and it's called an ion. This is for ions. Ions haven't been discussed yet. That's coming later. Ions versus isotopes. Sometimes people get ions and isotopes confused. Ions have a mismatch of protons and electrons. Mismatch of protons and electrons. And so we don't have electrical neutrality. And the elements here, we have a match. The number of protons is equal to the number of electrons. And therefore, the positive charge is balanced by the negative charge. In other words, the charge is neutral. All right, so here we have the symbol. Up here we have A, which is the number of protons plus the number of neutrons. Down here we have the number of protons. In other words, this is the mass number, which is called A. And down here is the atomic number, which is called C. SY is the symbol that we use to abbreviate the element. That's 1 or 2 letters here. And so we take a look at an example here. Oxygen. Oxygen has 8 protons and 8 neutrons. That means this is oxygen 16. So I would write this as O16 for oxygen, hyphen 16. Okay, and then we can get its composition based on that. So let's take a look at carbon 12 and carbon 13. Okay, carbon 12 and carbon 13, like that. The 6, well, carbon's element number 6, so I'm not even going to bother writing 6 down. Okay, so carbon's element number 6, which means it's going to have 6 protons. Okay, carbon 12 has how many neutrons? 6 neutrons. We can get that, because 6 and 6 is going to equal 12 here. And then how many electrons? 6 electrons. Carbon 13 has the same number of protons, 6 protons, but it has a different number of neutrons. 7 neutrons. How many electrons? 6 electrons. And so both of these have 6 protons. And so if it has 6 protons, then it's carbon. If it has 7 protons, then it's nitrogen. If it has 8 protons, it's oxygen. And so the number of protons is going to dictate what element we have. But the situation is now the number of neutrons. Did you know today, did you eat something today? Was it organic material, or was it rock, sand, or stone, or something like that, minerals? It was organic material? Then you ate some carbon 13 today. Could you taste the difference between the carbon 12 and the carbon 13? Is your body going to metabolize them differently? No. And so this is going to have the same chemical property. Same chemical property. It's carbon with 6 protons and 6 electrons. Same chemical property. However, their physical properties can be different. Now, the carbon that you eat, the carbon that's in nature, that carbon's going to have about 1%, carbon 13. And the carbon 13s are a little heavier. So, physical properties, mass. Carbon 13 weighs more. weighs more by about 1 unit because a neutron weighs about 1 atomic unit, and therefore it's going to be about 1 unit heavier. Not exactly, because it's not exact. The mass number, a lot of people get the mass number confused with the mass. The mass number is not a mass. This is not a mass. It's close to the mass, because do the electrons weigh much? Electrons don't weigh much. And so if a proton weighs about 1 U, a neutron weighs about 1 U, and an electron doesn't weigh much, then oxygen 16 is going to weigh about 16 U. Carbon 12 is going to weigh, you would say it should weigh about 12 U, but carbon 12 is special. We're going to talk about that. Carbon 13 weighs about 13 U. Now, the situation is how much does a U weigh? What does 1 U weigh? Did I talk about that? Do they have a 1 U mass made up of platinum and iridium locked in some vault in France?
Yeah, it's an exact storm.
Yeah, but it's not a 1 U though. It's a 1. Oh, is it? Well, the problem is platinum weighs, 1 single atom of platinum weighs a heck of a lot more than 1 U. 1 single atom of platinum weighs about 200 U. A single atom of platinum. And so what you have to do is you have to slice it. It weighs 200 U. You got to slice it into 200 pieces, and one of those pieces would be 1 U. So maybe did they slice a platinum atom in 200 pieces? No, impossible. So did I talk about this at all yesterday? Or did I not? How is the U defined? Okay, let me jump ahead here really quick. How is the U defined? You need to know how the U is defined. This is it. They can't lock anything in the vault in France because there is nothing that weighs 1 U. Absolutely nothing that weighs 1 U. And so why the heck did they pick 1 U? It's ridiculous, right? But it turns out it's not ridiculous. The reason they picked it is because they didn't define 1 U. You know what they defined? They defined 12 U. So look at the last part, 12 atomic units, 12 U. And so this is what they said. They said that a single carbon 12 atom is, since we can define the scale any way we want, just like the Celsius, we can define the Celsius, or I can make a new temperature scale. Maybe I'll make a new temperature scale with finer increments, finer steps. Okay, so what they did was, this is called an arbitrary definition. What they did was they took carbon 12 and let's say, okay, whatever that weighs, I'm going to call that exactly 12 U. And so there's nothing that weighs. Now, okay, that's fine. Now I know how a U is defined. So do they have a carbon 12 atom locked in some vault in France? They don't. You know why? Because it's cheap and it's available everywhere. You can get carbon atoms off. Probably the easiest source of carbon atoms is pencil lead. Pencil lead is made out of graphite. Graphite consists of carbon 12 and carbon 13, mostly carbon 12. And so it's cheap, and you don't have, are they going to lock up a piece of pencil lead in a vault in France? No, definitely not. And so all you do here is you take the lead, and then we have to weigh the atoms. Now, how do you weigh single atoms? Is it possible to weigh a single atom on a balance? Impossible. Well, they weighed electrons. How do they weigh single electrons? Yeah, it was kind of the plum pudding, but it was not. It was before that. It was this CRT. You remember the CRT? How they weighed single electrons is by using the CRT and. Did I show that video? Did I show the CRT video?
Was The bottle?
The bottle, yeah. They use the CRT and the magnets, yeah, and some physics. Well, that's how you weigh atoms. And so you're going to weigh atoms basically. It's not going to be a Coke or a soda bottle, you know, drilled out with a old refrigerator pump there they used for vacuum. Some people try to use house vacuums to try to suction out the air out of those things, but it's not powerful. Our vacuum's weak. This vacuum, we have a single pump for all these. This vacuum, I measured it. This vacuum was like, I think it was 2/3 of an atmosphere was the pressure measurement. And so it's like 10 psi. Out here is 14.7. This was about 10 psi. And so a little bit of vacuum, but not much. It's a very weak vacuum. I tried to do the marshmallows with this vacuum. It didn't work. It failed. It was too weak. But anyway, that's our house vacuum. So what we do is we put it in a container, and then how do you get the carbon atoms to form a beam? How you get the carbon atoms to form a beam is by hitting it with a laser. You hit it with a laser, it vaporizes some of the atoms off, breaks off the atoms off the surface. So now we have carbon-12 atoms in the gas phase. And then you get something like an electron gun. How do you make an electron gun? You make an electron gun like a CRT. You know, basically you saw an electron gun. CRT is an electron gun. You shoot electrons at the carbon-12 atoms, and what happens is that creates a charge. You know, a mismatch. You know, a charge is a mismatch, and sometimes an electron attaches, sometimes an electron knocks an electron off, and so we create charged carbon-12 atoms. If we create charged carbon-12 atoms, then we can accelerate those to, you know, if they're positively charged, they're going to be accelerated to a negative plate. If they're negatively charged, they're going to be accelerated to a positive plate. And so we accelerate the atoms like this, and then put a magnet there and see how much they're deflected by, like this. So you can try with a Coke bottle, but it's not going to be very effective. In fact, they sell these machines commercially. They're called mass spectrometers. So we use a mass spectrometer, which essentially works like that Coke bottle, and it measures the mass of the atoms based on the angle of deflection of the atom. And so if you have a mass spectrometer, what's going to happen is it's going to hit, carbon-12 is going to hit here. So if carbon-12 hits here, boom, then you know that's exactly 12U by definition. And then the other, carbon-13 is going to hit slightly above it. And so if carbon-12 is exactly 12, then we can measure how much carbon-13 is. Is carbon-13 going to be exactly 13? No. No, it's not. It's not. And so we use a mass spectrometer. This is the output for neon. Neon 20 hits here, neon 21 hits here, neon 22 hits here, the detector, after being deflected by the magnet. It looks like neon consists of mostly neon 20 isotope. Not much neon 21 and not much neon 22, but there are 3 isotopes for neon that occur. Can you tell by looking at the periodic table that there are 3 isotopes? No, you can't. Can you tell that there are 2 isotopes for carbon? There's actually a third one. The third one is carbon-14, but it's radioactive. Not including, these are the naturally occurring ones here. We don't, and so, well, of course we'd like to use theory to predict it. You know, can you use some theory to predict how many isotopes I'm going to see for lead? That way I don't have to memorize it, or look it up. Well, you know, the nuclear physicists are working on it. The nuclear physicists are working on the theory that the allow predictions. Actually, they already have some theories developed to try to allow predictions such as that. Instead, all this is theoretical prediction or experimental observations. All this is experimental observations. And so here, carbon-12 weighs exactly how much? 12U. Therefore, when we measure carbon-13 on the mass spectrometer, it comes out to 13.0033548,378. You know, that's a heck of an expensive mass spectrometer to get that kind of precision. Used to be, mass spectrometers would give you 6 decimal places. A mass spectrometer giving you 6 decimal places is big bucks, Well, we have one. I think that gives us 6. That's $50,000 right there. Well, now they're cheaper. A lot of instruments. Now they can put mass spectrometers in small ones, but they aren't this precise. But this is very precise, which means very sensitive. You can measure very minute mass differences that this can measure, which is pretty impressive. But anyway, once we calibrate it, we got to calibrate our mass spectrometer. Once we calibrate it, then we can measure all these others. And this is a good source for calibration because you don't have to go to France and get some carbon-12. It's readily available for everyone. Although it would be nice to be able to go to France to get some carbon-12. It wouldn't be necessary. But you can see here, hydrogen, there are 2 isotopes. There's a third one called tritium, which is radioactive. Helium, there are 2. Beryllium, how many isotopes are there? Only 1. That means all the beryllium atoms are exactly the same. So Dalton would have been right. If he said all beryllium atoms are identical, he would have been right because all beryllium atoms are identical. All beryllium atoms have how many protons? 4. How many neutrons? 5. And how many electrons? 4. That would be 100% of the beryllium atoms there. However, he would have been wrong if he said oxygen. How many different isotopes are there for oxygen? 3. There's oxygen 16, which weighs almost 16. It's 15.9949146221. There's oxygen 17, which weighs almost 17, and there's oxygen 18. 0.205% of the water you have today contains 0.205% of the water you have today contains oxygen 18. However, this fractionates because if you go deep under the ocean, which one do you expect to find more? The heavier ones or the lighter ones?
The heavier ones.
The heavier ones. And so this is called isotopic fractionation. Geologists love this because as you go down, the composition changes. You get more oxygen 18 down here than up here. It's very easy to tell if ozone was produced by smog down here versus ozone in the ozone layer because ozone in the ozone layer has much more oxygen 16 or oxygen 18?
16.
Oxygen 16 than the ozone down here. The ozone down here has much less oxygen 16. And so this isotopic fractionation is used and the mass spectrometer is an easy tool to use to determine that. And so these numbers here are just averages. The average is 0.205, but you're going to see differences depending on your location. Radiocarbon dating makes use of isotope fractionation or percent ratios in isotopes like carbon-14 ratio. Okay. But anyway, we need a table like this. This is called a table of isotopes, which shows the masses and the percent and what isotopes are found in nature. And they're much bigger tables than this. They're located in chemistry reference books. One big chemistry reference book, which has all of them, or practically all of them, is called the CRC, the Handbook of Chemistry and Physics. So we need to know how the U is defined. Do you need to know how the dozen is defined? Who defined the dozen? How is it defined? Do you need to know that? No. So we don't care. Actually, I have no idea how the dozen is defined. I know it's 12, but it doesn't come from carbon-12. The dozen came from something else.
How would you read that 1U, that space, right under atomic mass?
How would I read that? I wouldn't read that. It's crazy. I'm sorry. I didn't correct these slides. These are the slides as given by the publisher, the ones that are on the publisher's website. But I would fix it. This is a typo. 1U is defined as, so these 3 lines are supposed to be in the middle here, because when you have 3 bars like that, that means by definition. And so 1U is defined as 1/12 of the mass of a carbon-12 atom.
That makes sense.
Can you slice a carbon-12 into 12 pieces? No, you can't. So we just define it like that. But it would be exactly 1U would be 1/12. Unfortunately, we can't slice a carbon, and unfortunately, there's nothing. The closest thing that we have to 1U is what? No. The closest thing that we would have to 1U would be 1U of mass would be, I don't know if you caught this. Hydrogen. This is the species that's closest to 1U, but is it exactly 1U? No. And there's nothing else closer. I mean, what else would be closer? Like half a helium? Half a helium would give you 1.5, maybe a third of a helium, but we can't take a third of a helium. There's nothing else. What's matter made of? Atoms. We can go subatomic. If we go subatomic, I didn't give you the masses of the subatomic particles. I need to give you the masses. A proton's very close, 1.0076. I'll give you the masses later. Okay, getting back to this. So that means the water that you drank today consists of different combinations of atoms. Water consists of hydrogen, oxygen, hydrogen. And I'm going to show these dashes to show that they're connected. That connection is a bond. And so they're bonded together. Hydrogen, oxygen, hydrogen, like that. And so we have some possibilities. The possibilities are, we have how many choices of hydrogen? Two. And how many choices of oxygen? Three. And so we're going to build these things like little model blocks. And so what are the possibilities here? The first possibility is the first hydrogen, we say, is a hydrogen 1, and the second hydrogen is a hydrogen 1. Okay, but that means the oxygen, well, how many choices do we have for oxygen? 3. And so the first one will make oxygen 16. That's one choice. And so I'm going to keep the oxygen the same here. And so if I keep oxygen 16, the next choice is the first hydrogen is a hydrogen 1, but the second hydrogen will be a hydrogen 2. What's the next choice?
First one is 2.
Yeah. Hydrogen 2. We'll go 1. 2, 16, 1. And then we'll go 2, 16, 2. Let's see how much these weigh. Just not exactly, because if I want to know how much these weigh, I'd have to add it up. So actually, let's go ahead and do it precisely. So if I want to know how much this weighs, I need 2 at 1.00782503321 U. And then oxygen 16 weighs how much? Oxygen 16 weighs 15.9949146221 U. And so let me grab a calculator here. Let's go ahead and do that really quick. And so I'm going to go 2 times 1.00782503321. Hopefully this calculator is not good. Let me use this one. 2 times 1.00782503321 equals, all right, plus 15.9949146221. You know what? My calculator doesn't hold that many digits. My calculator's got to round it. My calculator only holds 10 digits. How many does yours hold? Can you enter all 11 numbers? Or no, 10 numbers plus decimal? No. Anybody have a calculator that holds more than 10 digits?
I mean, yeah, it'll just give it to me in the scientific notation.
Even in scientific notation, it won't. Will it hold more than 10 in scientific notation? How many decimal places am I allowed in this calculation? Two, 4, 6, 8, 10. 2, 4, 6, 8, 10. I'm allowed 10 decimal places in this. How many decimal places did my calculator give me? 2, 4, 6, 8. My calculator only gave me 8 decimal places. What did my calculator do? Rounded. And this is well known. Calculators are well known to do round off error. This is why the Casio tries to avoid. Did anybody buy the Casio FX115? It's a hassle, but the Casio gives you the answer in a fraction. The Casio gives you the answer in a fraction because if you have to do a next step, it has no round off error. That number has all the decimal places because we don't have to convert it to a decimal. So the Casio is very good. It's a very powerful calculator because it minimizes round off error. Whereas something like this is going to round it at the 8th decimal place, which is going to lead to an error in the final calculation. So if you calculate it using this calculator versus you calculate it using Casio, you might get the different answer, surprisingly. But anyway, unfortunately, my calculator rounded off to 8, and I do have the Casio, but it's still got to round off. The Casio is going to round off at the end, but it won't do intermediate round-offs unless you leave it in fractional form, and then we don't have to worry about it. Okay, so that's the reason for fractions. So how much does it weigh? 18.0, that's that. And so you know what this is about, 18U. About 18U. How many U is this about? Because I don't want to hassle with adding it up. So how much does a H1 weigh about? 1 U. How much does an O16 weigh about? And how much does an H2 weigh about? 2 U. And so this would be about 19 U. This one would be about 19 U.
Wouldn't that be the same atom though?
Okay, that's a good question. Are these two the same molecule? They are. You can't tell the difference. They're exactly the same. But in terms of statistics, we have to keep track. It's a second way of making it. If it's a second way of making it, we're talking in terms of percentage abundance. We have to factor that in as far as the percentage abundance goes.
If you have like, let's say sulfur is 36, and you have 35.966 or 967 is the mass. How many? If you're trying to say, oh, okay, it's number 16, so it has 16 protons. How many neutrons would it have? Would you round up to 36 like they do in the symbol?
No, we don't get the number of neutrons from this. We get the number of neutrons from this.
So, but you round up because they rounded 35.
No, we don't round it. These two numbers are different. The
Okay.
mass number and the mass are two totally different thing. This is why I wrote down earlier, I wrote down the mass number is not the mass. The mass number is the number of protons plus the number of neutrons. The number of protons plus the number of neutrons is exactly 36. The mass is about 36. The mass number is exactly. Some people do this. What you're saying is
How
we
do
should.
you know the number of neutrons are just looking at the periodic table?
We can't. Can't tell. We can tell approximately how many, but we can't because we don't know how many isotopes there are. So we can always tell approximately. So what you're saying is this is the symbol here, 35.967, which they round to sulfur 36. That's not the case.
Okay.
Yeah. This number did not come from that. This number just came from the proton and neutron. Let's see another example here. Anyway, they're always going to be close. And so if I look at the combined mass number, the sum of the mass numbers is 1 plus 16 plus 1, which gives me 18. That means I have a total of 18 protons and neutrons in this molecule. If I look at the mass number here, it's 19. Here it's 19. Here it's 20. But the mass is different. The mass of this is going to be about 20 U when we add it up. The mass number is exactly 20. All right, what were the other molecules that we did? And so these two are the same. So what were the other molecules? Yeah. Well, we're going to have H1O17, H1, H1O17, H2, H2O17, H1, H2O17, H2. If you look at it, we can say the same thing here. These two are going to be the same. And what are the approximate masses going to be? This is going to weigh about how much? 19 U. This one?
20.
About 20 U. This one?
20 U.
U.
20.
All right, finally we have H1O18. H1, H1O18, H2, H1, oh no, not H1, H2O18, H1, H2O18, H2. Again, these are the same here. And so what are the approximate masses here? The mass of this one?
20.
This one?
21.
This one?
21. 22.
And so what was the lightest water molecule you consumed today? H1O16H1. How much did it weigh about? 18 U. What was the heaviest water molecule you consumed today? H2O18. H2. That was the heaviest one. And how much did it weigh? About? A single molecule of that weighs about 22 U.
How about
H3 is, the abundance of H3 is very, very small. And H3 is radioactive. And so even if you had it, it would decay unless you're constantly producing it. So the amount changes as well. Carbon-14 is a little different because it's continually produced.
So in the ocean, these molecules, they
In the
sort of
ocean,
stratify.
a little bit, yeah. And so in the ocean, the same thing would happen. They would stratify. We call it fractionation. And so you'd see but in something like this, how many different water molecules did you consume today? How many different water molecules did you consume today? 9. And what is the average mass of the water molecule that you have? You'd say, oh, if it goes from 18 to 22, the average would be 20. Right? The average of 18 and 22 is 20. But it's not correct. You know what the average mass of the water molecule you had today is? Is 18.02 U. That's the average. Now, how can the average be 18.02 U? Is that even possible? If you take something that ranges from 18 to 22, how can the average be 18? Just slightly above 18. Yeah, it has to do with the percentages here. You know, this is called a weighted average. And the weighted average is this. Most, nearly all, 99.99% of the water molecules you had today were only this. So when I ask you how many, you drank mostly this and a tiny bit of all the others. Tiny bit. And so that means the average water molecule weighs much closer to 18 than all these others. Does that make sense? Yeah. And so it's called a weighted average. And so this is a hassle. You know, do you want to do this for every molecule out there? Carbon dioxide. How many carbon dioxide molecules do you exhale? Well, we have oxygen 16, carbon 12, oxygen 16. We have oxygen 16, carbon 13, oxygen 16, etc. And so when we look at it in that, at the particulate level, this is how we have to visualize water. At the particulate level, we must visualize water like this. Because if you're working with a single water molecule, then you need to know which one is it. You can't take the average. You'll find no such thing. The average does not, a water molecule with this mass doesn't exist. And so what we're going to do here is this. We're going to be working with macroscopic. For macroscopic, or microscopic, we want to use the averages. And so here, hydrogen 1 weighs about 1 U, hydrogen 2 weighs about 2 U. The average would be 1.5. You know, the average between 1 and 2, 1.5. But this is a weighted average. Which one is much more abundant? Which one? Hydrogen. When we look at the percentages, in nature, 99.9885% of all hydrogen atoms are hydrogen 1. Therefore, the average is going to be very close to 1. That's what we see here on the periodic table. On the periodic table, let's take a look at a hydrogen. Now, this is not a good periodic table. Let me get a better one. So what's this number up here? Z, or the element number. What's this number down here? This is the average mass of a hydrogen atom. Do they have enough room to list all the individual masses? No. Do they have enough room to tell you how many isotopes of hydrogen there are? No. So that type of information is missing. The only thing they tell you is the average. Now, if you're working macroscopic, this is perfect. If you're working with single hydrogen atoms, this isn't going to work. We ignore this number and look at instead the individual masses for hydrogen 1 and the individual mass for hydrogen 2. And so, what is the average mass of a lithium atom? 6.941. Can you find a lithium atom in nature that weighs 6.941? No, there are no such thing. No such thing as a lithium that weighs 6.941. Instead, that's the average. Well, that's the average for what? I don't know. That's just the average. And so we got to find out where did that average come from? That average came from a table like this. Except I didn't have lithium. And so I should have picked something else. Let's pick something else.
Nitrogen.
Nitrogen. All right. We look at nitrogen. What's the average weight of a nitrogen atom? 14.00674. It's hard to read. That's 14.00674. Are we going to find a nitrogen that weighs that much? Yes or no? No, we are not going to find a nitrogen. Why? It's the average. And so we look. Nitrogen. Nitrogen 14 weighs 14.003. Nitrogen 15 weighs 15.00. The average is 14.9. What was it? Which means we should have much more, or 14.0 whatever, close to 14.01. I actually haven't memorized 14.01. So it's much closer to 14 than 15. In fact, if it's 14.01, it's 99%. If the average is 1450, then it would be 50%. If the average is 14.90, it'd be 90%. Of nitrogen at 15. So it's a weighted average. So is that clear what the number means? Okay, now I'm going to ask you this. What's the average mass of phosphorus? Mass of the average.
30.
There it is. Phosphorus. What's the average mass of phosphorus? 30.973762. Are you going to find any phosphorus atoms in nature that weigh 30.97? No. Why? It's the average. So we go over here, and that's a trick question because I trained you to think incorrectly because I was thinking it'd be easier. But there's a problem. I should have went to fluorine. There's a problem because do you know what? Even though it's not shown here, all atoms of phosphorus weigh that much because there's only one isotope. And so we talked about this for beryllium here, but there's another one. Do you see what else has only one isotope? Phosphorus is another, and another is fluorine. 100% of the atoms weigh that, and so the average is just going to be 18.99. And so all of these atoms weigh this much. Does that make sense? And so that I was tricked you. Sorry. The trick was, but then you go, well, how can you tell? The only way you can tell is you have to look it up or have it memorized. But in fact, it's not that common. So fluorine, yes. Beryllium's not common. Beryllium's not common because beryllium is highly toxic, super toxic, so we don't really worry about it. So fluorine and phosphorus are the two big ones that we worry about. Fluorine and phosphorus have only one isotope.
Do you know exactly how many elements in the periodic table?
That's a good question. Do I know exactly how many elements in the periodic table have only one? No, I don't. I never counted that. I never counted that because the only time I worry about this is when I'm working with individual isotopes, and the only time I'm working with this with individual isotopes are for the elements that I'm interested in, but I never looked it up. I mean, we could figure it out because if you go to a book, a reference book, do you know what the reference book is called? CRC Handbook of Chemistry and Physics. Ooh, it's cheap. You have to be careful. You know, $15.85, that's a pretty good deal for the 2000. That's you know, it's pretty good. 2005, 2006 edition is pretty good. Because if you buy the latest edition, let's see how much the latest edition is. I guess we're on the 91st edition. So if you buy the latest edition of this, that's $185, the 99th edition. Regular price is $229.95. But this one, you could find the latest data with the most sig figs. This is updated every year, and so it's good. That one's a good one. The other good handbook is called the Merck Index. Merck Index is quite a bit cheaper, but the Merck Index is, has a different slant. The Merck Index is mostly for drugs and biologicals. Obviously because Merck is a drug company, but this book is very useful for many things, not just drugs and biologicals. There's a lot of good data in there. Good review. And so those are two places you can look. Of course we can just search. We can search a table of isotopes. And then we can just look. You know, if we have a comprehensive enough table, then we can see how many isotopes there are for particular elements. This is not it. But there. All right, so let's go back to this here. So the first thing is we're going to figure out how to calculate a weighted average. You know how to calculate a weighted average? There are different equations that we can use to calculate a weighted average. First, we will have something called the average atomic mass. The average atomic mass is just called the atomic mass. But, you know, whether you find an atom that weighs that much depends on how many isotopes there are. And so to differentiate this, then we'll have the atomic mass. The atomic mass, we're not going to call the atomic mass, we're going to call this the isotopic mass. The isotopic mass is the mass of a specific isotope, like H1, H2, etc., even H3. And so the atomic mass, which is the average atomic mass, is going to be called, so atomic mass is equal to, there are different ways you could do this. You could do decimal or fractional abundance. Decimal or fractional abundance of isotope 1 times the mass of isotope 1 plus isotope 2, we just repeat. Plus, etc. And so we're just summing up the decimal or fractional abundance times the mass. And so let's do a couple of quick calculations here. The natural distribution of isotopes of boron is 19.9% at boron 10 at a mass of 10.0129370 U, and 80.1% boron 11 at 11.09305 U. And so here, we can do 19.9 out of 100, or 0.199 times the mass, 10.0129370 U Okay, that's isotope 1, then we go on to isotope 2, so it's 80.1 out of 100. I'd like to do it this way, but I'm going to use some decimal. 80.1 out of 100 times 11.0093055 U. And so we punch in the calculator here. And so they'd like to use a decimal rather than the fractional abundance. And so rather than 19.9 out of 100, they wrote 199 times the mass gives that. But they, they're keeping track of sig figs, because how many sig figs am I allowed here? 3. So they got 1.99 U. Okay, then I do the next step. The next step is to take the decimal, or the fractional abundance of isotope 2, and 80% this, so 80% of that mass is 8.82. 3 sig figs here. Okay, now what we have to do is an addition. So this is why they're doing the multiplication first, and then figure out how many decimal places, and then do the addition, and we're allowed how many sig figs for a final answer? 3 or 2 decimal places. In this case, it's 3 sig figs, 2 decimal. How did they get 4? Is that right? Is that wrong? How did they get 4? Did they make a mistake here? It turns out they didn't make a mistake. They got 4 sig figs, 10.81. U is the average. It's 4 sig figs. When we say we should expect 3, this is 3 sig figs. This is 3 sig figs. Shouldn't we get 3 sig figs in our final answer? Is it because there's a 0 out there? No, it's not because of that. Because this is still counted as significant. So that's 1, 2, 3, 4 sig figs. Whether it's a 0 or non-zero, it doesn't matter because there's a decimal place. If there was a 0 like this, then it's insignificant. But because of the 1, it makes it significant. And the decimal place. So that's 4 sig figs. And so I think a lot of people said 3 sig figs. Why did you say 3 sig figs? Why you said 3 sig figs is because that's what you would expect using the rules for multiplication and division, but for addition and subtraction, we shouldn't say sig figs, and I baited you on that because I said how many sig figs. I should have said how many decimal places. How many decimal places are you allowed in your final answer? And the answer is 2. I don't care about the sig figs. You shouldn't care about sig figs when you're doing addition and subtraction. You should only care about decimal places. And so we end up with 4 sig figs. That's correct. Our final answer should have 4 sig figs. All right, there are only 2 isotopes. If there's a 3rd isotope, then we just add the 3rd one. The 4th isotope, add the 4th one. Naturally occurring lithium is composed of 2 isotopes. 7.59% 6 and 92% 7. So it's about 10% 6, 90% 7. I can already do the average. The average is going to be 6.9, roughly. It should be 6.9. But to get a more accurate number, I'll do the calculation. 6.9 is 90% towards 7, so that's why I got 6.9. And so we just plug it in. It comes out to 6.9. But that's how we can check on certain things. So for example, chlorine. Chlorine's a good one as a check. Chlorine is about 35%. No, sorry. Chlorine is 75% 35 and 25% 37. What's the average? Okay. Now, if it's 50-50, it would be, the average would be 36. 36 is about halfway between those two. Do you see that? So it's going to be, the average is going to be closer to, 35. And it'd be 35.5, the average. Let's see if there's an easier one. No. Actually, if that didn't make sense, just forget it, because that's more just doing a calculation in your head and getting a rough answer, approximate answer, rather than an accurate answer. Oops, I forgot the break. Let's take a break and then we'll start again. Almost done.